stock prediction. This project introduces common techniques to manipulate time series and make predictions. The data is a sample from the historical. Only the new German fund, GF, will be considered for analysis. There are roughly 1,000 days of record trading for GF. Clean data. This code is importing various libraries and functions that will be used for data analysis, visualization, and modeling. Step by step, the code does the following. 1. Imports the NumPy library, commonly used for mathematical functions and arrays, and assigns it the nickname NP. 2. Imports the pandas library, commonly used for data manipulation and analysis, and assigns it the nickname PD. 3. Imports the matplotlib.pyplot library, commonly used for creating visualizations, and assigns it the nickname PLT. 4. Imports the Seaborn library, commonly used for statistical data visualization, and sets the default style to be used. 5. Imports various error metrics from the scikit-learn library, commonly used for machine learning, such as R2_score, median _absolute error, mean _absolute error, median _absolute error, mean _squared error, and mean squared log error. 6. Imports the minimize function from the scipy.optimize library, commonly used for numerical optimization. 7. Imports the TSA module from the statsmodels library, commonly used for time series analysis. 8. Imports the API module from the statsmodels library. 9. Imports the tqdm_notebook function from the tqdm library, commonly used for creating progress bars in Jupyter notebooks. 10. Imports the product function from the itertools library, commonly used for creating combinations or permutations. 11. Defines a function named mean_absolute_percentage_ error, which calculates the mean absolute percentage error between the true values and predicted values. 12. Sets a warning filter to ignore any warning messages that might be generated by the code. 13. Sets the matplotlib backend to display visualizations inline within Jupyter Notebook. This code is assigning the file path data/stock_prices_sample.csv to the variable data path. This code reads a CSV file located at datapath using the pandas library. The CSV file is assumed to have a date column, which will be used as the index column. The date column is parsed as dates using the parse_dates parameter. After reading the CSV file, the code displays the first 10 rows of the data frame using the head method. The code data.shape retrieves the shape of the data, which refers to the number of rows and columns in the data structure. This information is stored in the shape attribute of the data object. In short, this code returns the dimensions of the data, the number of rows and columns. The code data.types is used to get the data types of each column in a dataset called data. Here's a step-by-step explanation. 1. Data refers to the dataset that contains the data you want to examine. 2. .types is a method that can be called on a data frame, a data structure in pandas library, to retrieve the data types of its columns. In short, this code retrieves the data types of each column in a dataset named data. This code filters a data set called data by removing any rows where the value in the ticker column is GF. It then removes any additional rows where the value in the type column is intraday. The code data.head is used to display the first few rows of a data frame object named data. Here is a step-by-step explanation. 1. The code accesses the head method of the data object. 2. The head method is a built-in function in pandas library that retrieves the first few rows of a data frame. 3. By default, head returns the first 5 rows of the data frame. 4. The result of the head method is printed to the console. It will display the first few rows of the data frame, showing the column names and corresponding values. This code drops specified columns from the data frame named data. 1. A list of column names to be dropped is created and assigned to the variable drop_calls. 2. The drop function is called on the data frame with the following arguments: a. Drop_calls, the list of column names to be dropped. b. Axis equals 1, specifies that the columns are to be dropped. c. In place equals true, indicates that the changes should be made to the data frame itself. 3. The specified columns are then dropped from the data frame. The code data.head is used in Python to display the top rows of a dataset. 1. It is assumed that the variable data refers to a dataset or a dataframe object. 2. The .head function is called on the data object, which returns the first few rows of the dataset. 3. By default, the .head function returns the top 5 rows of the dataset. 4. The output of this code will be the first few rows of the dataset, which can be used to quickly inspect the data and get an idea of its structure and contents. Exploratory Data Analysis, EDA. This code uses the matplotlib library to plot a line graph. The first line plt.figure, fig size sad face 17, 8, sets the size of the figure, graph, to be plotted. The next line plt.plot, data.close, plots the data from the close column of the data frame on the graph. The next line plt.title, closing price of New Germany Fund Inc., GF, sets the title of the graph to closing price of New Germany Fund Inc., GF. The line plt.alabel, closing price, $, sets the label of the y-axis to closing price, $. The line plt.zlabel, trading day, sets the label of the x-axis to trading day. The line plt.grid, false, turns off the grid lines on the graph. Finally, the last line plt.show, displays the graph. Moving average. This code is for plotting a moving average trend line in a time series data. Here is a step-by-step explanation of what the code does. 1. The function plot_moving_average takes in 4 parameters: series, the time series data, window, the size of the moving average window, plot_intervals, a boolean indicating whether to plot confidence intervals, and scale, the scale factor for the confidence intervals. 2. The code calculates the rolling mean of the series using the rolling function from the pandas library. It sets the window size for the rolling mean to the value of window parameter. 3. It creates a figure and sets the title of the plot to include the window size. 4. It plots the rolling mean trend line using the plot function from the matplotlib library. The trend line is plotted in green color and labeled as rolling mean trend. 5. If the plot_intervals parameter is set to true, the code calculates the mean absolute error, MA, and standard deviation, between the actual values of the series and the rolling mean. Then it calculates the upper and lower bounds of the confidence intervals as the rolling mean plus, minus the sum of MA and scale times deviation. 6. It plots the upper and lower bounds as dashed red lines. 7. It plots the actual values of the series starting from the window index. 8. It adds a legend to the plot, positioning it at the best location, and displays the grid. Overall, this code is useful for visualizing the trend in a time series data using a moving average approach and optionally showing confidence intervals around the smoothed values. This code is calling a function called plot_moving_average and passing 2 arguments to it, data.close and the number 5. The function is likely designed to plot a moving average of the closing prices in a dataset. To calculate the moving average, it takes the previous 5 days, or 1 week, of closing prices and averages them. This process is repeated for every day in the dataset, resulting in a smoothed line representing the average closing price over a week. The function then plots this smoothed line, allowing for a visual representation of how the closing prices have been trending over time. This code calls a function named plot_moving_average and passes 2 arguments to it, data.close and 30. The function plot_moving_average calculates the moving average of the data.close values over a period of 30 days. It then plots the moving average on a graph. This graph helps in visualizing the trend or pattern of the data.close values over time. This code is calling a function called plot_moving_average and passing in 3 arguments, data.close, 90, and plot_intervals equals true. The first argument, data.close, suggests that we are working with a dataset that contains a column named close. The second argument, 90, specifies the window size of the moving average. In this case, it is set to 90, which means we are calculating the moving average using the previous 90 data points. The third argument, plot_intervals equals true, indicates that we want to plot the intervals around the moving average. Overall, this code is applying a smoothing technique to the data using a moving average with a window size of 90 days and visualizing the result with an optional interval plot. Exponential smoothing. This code implements exponential smoothing on a series of data points. Exponential smoothing is a time series forecasting technique that calculates a weighted average of past values to make predictions. Here is a step-by-step explanation of what the code does. 1. The function exponential_smoothing takes two inputs, the series of data points and the alpha value which determines the weight of the current data point in the smoothing calculation. 2. The variable result is initialized as a list containing only the first value of the series. This initial value is assumed to be the first prediction in the smoothed series. 3. The code then enters a for loop that iterates through the rest of the series, starting from the second data point, index 1. 4. Inside the loop, the code calculates the next prediction by taking the weighted average of the current data point and the previous smoothed value. This is done using the formula, smoothed_value equals alpha asterisk current underscore data underscore point plus 1 alpha asterisk previous underscore smoothed underscore value 5. The calculated smoothed value is then appended to the result list. 6. After the loop finishes, the result list, which now contains all the smoothed values, is returned as the output of the function. This code is a function that plots the exponential smoothing of a given series of data. Here is a step-by-step explanation. 1. The function takes two parameters, series, which is the input data series, and alphas, which is a list of alpha values, smoothing constants, to use for the exponential smoothing. 2. The function begins by creating a new plot figure with a size of 17 inches by 8 inches. 3. It then loops through each alpha value in the alphas list. 4. For each alpha, it calls another function called exponential_smoothing, passing in the original series data and the current alpha value. This function calculates the exponential smoothing using the given alpha. 5. The function then plots the calculated exponential smoothing values on the current plot figure, adding a label that indicates the alpha value used. 6. After plotting all the exponential smoothing lines, it plots the actual values of the series data as a cyan line. 7. It then adds a legend to the plot, placing it at the best position. 8. It adjusts the axis limits to tightly fit the plotted data. 9. It adds a title to the plot, indicating that it is showing exponential smoothing. 10. Finally, it adds a grid to the plot and displays the plot. This code is calling a function called plot_exponential_smoothing with two arguments, data.close, and a list containing the values 0.05 and 0.3. Step by step, this is what the code does. 1. The function plot_exponential_smoothing is called. 2. The first argument, data.close, is passed to the function. This indicates that the function expects a variable called data with an attribute called close. 3. The second argument, 0.05, 0.3, is passed to the function. This indicates that the function expects a list containing the values 0.05 and 0.3. 4. The function, plot_exponential_smoothing, performs certain computations or actions using the passed arguments to produce some kind of visualization or output. The specific details of what the function does can only be determined by examining the code within the function itself. Double exponential smoothing. This code implements the double exponential smoothing technique to forecast future values based on a given series of data points. Here is a step-by-step explanation of the code. 1. The function double_exponential_smoothing takes three arguments, series, representing the input series of data points, alpha, representing the smoothing factor for the level component, and beta, representing the smoothing factor for the trend component. 2. The variable result is initialized as a list with the first element of the input series, series 0. 3. A loop is started from 1 to the length of the series, len, series, plus 1, iterating over each position in the series. 4. Within the loop, there is a condition to check if the current position is the first, n == 1. A. If it is the first position, level is set to the first element of the series and trend is set to the difference between the second and first elements of the series. B. This step is necessary to initialize the values of level and trend for subsequent calculations. 5. There is another condition to check if the current position is greater than or equal to the length of the series, n = len, series. A. If it is, it means we are in the forecasting phase, and the value to be added to the result list is the last element of the result so far, result-1. B. This is done to keep the forecast aligned with the previous values. 6. If the current position is not in the forecasting phase, the value to be added to the result list is the value at that position in the series, n. 7. The variables last_level and level are used to store the previous and updated values of the level component for the current position. 8. The updated level value is calculated using the formula, level equals alpha asterisk value plus 1, alpha, asterisk, level plus trend. A. This formula takes into account the weighted average of the current value and the previous level value, adjusting it based on the smoothing factor, alpha. 9. The variable trend is updated using the formula, trend equals beta asterisk, level, last_level, plus 1, beta, asterisk trend. A. This formula calculates the updated value of the trend component, taking into account the difference between the current and previous level values and adjusting it based on the smoothing factor, beta. 10. The calculated value, which is the sum of the updated level and trend components, is appended to the result list. 11. After iterating through all positions in the series, the result list is returned as the output. This code is implementing a function called plot_double_exponential_smoothing. This function takes in three parameters, series, which represents the data series to be smoothed, and alphas and betas, which represent the smoothing parameters to be used. The code begins by creating a figure with a size of 17 by 8 using matplotlib.pyplot. Then, it iterates over each value in the alphas list, and for each alpha value, it iterates over each value in the betas list. Within the nested loop, it calls another function called double_exponential_smoothing to perform the double exponential smoothing operation on the series data using the current alpha and beta values. It then plots the smoothed data using plt.plot, with a label indicating the current alpha and beta values. After the nested loop, it plots the original series data using plt.plot and labels it as actual. It adds a legend to the plot, adjusts the axis limits to fit the data, sets the title as double exponential smoothing, and enables the grid. Overall, this code performs a double exponential smoothing operation on a given data series using different combinations of alpha and beta values. It then plots the smoothed data along with the original data to visualize the smoothing effect. This code is applying the double exponential smoothing technique to a dataset called data.close. The double exponential smoothing technique is a time series forecasting method that is commonly used to make future predictions based on historical data. The function being called is plot_double_exponential_smoothing, and it takes two parameters, data.close, which represents the historical data, and alphas and betas, which are arrays containing the smoothing factors. Here are the steps performed by the code. 1. The function takes the historical data points from data.close. 2. It applies the double exponential smoothing technique to these data points using the specified smoothing factors from the alphas and betas arrays. 3. The result of the smoothing process is then plotted on a graph to visualize the trend and forecasted values. In summary, this code applies double exponential smoothing to a dataset and plots the results on a graph. Stationarity. This code defines a function called xplot that takes in a time series data as input and plots various time series analysis plots. 1. First, the code checks if the input data is a pandas series. If it is not, it converts it into a series. 2. The code then sets the style of the plot using the BMH style from the matplotlib library. 3. It creates a figure with the specified fig size, default is 12 times 7. 4. It sets the layout of the plots in the figure to be a 2 by 2 grid. 5. It creates three axes for the plots, ts_ax for the time series plot, acf_ax for the autocorrelation function plot, and pacf_ax for the partial autocorrelation function plot. 6. It plots the input time series data on the ts_ax. 7. It calculates the p-value using the Dickey-Fuller test for testing stationarity of the time series, and sets the title of ts_ax with the p-value. 8. It plots the autocorrelation function on the acf_ax using the plot_acf function from the statsmodels library. 9. It plots the partial autocorrelation function on the pacf_ax using the plot_pac function from the statsmodels library. 10. Finally, it adjusts the layout of the plots and displays the figure. The code then calls the xplot function with the close column of a dataset called data as input and a lag value of 30. This code calculates the difference between each value in the close column of a dataset, data, and the previous value by using the shift function. Firstly, it calculates the difference by subtracting each value in the close column from its previous value using the data.close.shift 1 operation and stores it in the variable data_diff. Then, it calls the xplot function, passing in the data_diff series exclude the first value using data_diff 1 smiley face. The xplot function is likely a custom function or a function from a library used for time series analysis, which plots the time series data and shows the autocorrelation for specified lags, in this case, 30 lags. The code is essentially calculating the difference between consecutive values in a time series, and then generating a plot that displays the autocorrelation of this difference time series up to 30 lags. SARIMA. This code sets up ranges and initial values for various parameters. PS is a range from 0 to 4, representing values that can be used for a parameter called P. D is set to 1, representing a parameter called D. QS is a range from 0 to 4, representing values that can be used for a parameter called Q. PS is a range from 0 to 4, representing values that can be used for a parameter called P. D is set to 1, representing a parameter called D. QS is a range from 0 to 4, representing values that can be used for a parameter called Q. S is set to 5, representing a parameter called S. Next, the code uses the product function to create a list called parameters_list that contains all possible combinations of values from the ranges PS, QS, PS, and QS. Finally, the code uses len to determine and output the length of the parameters_list list. This code defines a function called optimize_SARIMA that takes in a list of parameters, integration order, seasonal integration order, and the length of the season. The function's purpose is to find the best parameters for a SARIMA, seasonal autoregressive integrated moving average, model. The function starts by initializing an empty list called results and setting the initial value of best_AIC, Algorithmic information criterion, to infinity. Then, the function enters a loop where it iterates over each parameter in the provided parameter list. Inside the loop, it tries to fit a SARIMAX model to the data using the current parameter values. If an exception occurs during this process, the loop continues to the next parameter. If the model fitting is successful, the function calculates the AIC value of the fitted model and stores it in the variable AIC. AIC is a measure of the model's goodness of fit relative to its complexity, with lower values indicating better fits. The function then checks if the current AIC value is lower than the current best AIC value. If it is, the best model, best AIC value, and the corresponding parameters are updated with the current values. After evaluating all the parameters, the function creates a data frame called result_table to store the list of parameters and their corresponding AIC values. The data frame is sorted in ascending order based on the AIC values. Finally, the function returns the resulting data frame. Outside of the function, the optimize_SARIMA function is called with the provided arguments, and the resulting data frame is assigned to the variable result_table. This code sets the parameters for the best SARIMAX model, seasonal autoregressive integrated moving average with exogenous factors, based on the lowest AIC, Algorithmic information criteria. Here is a step-by-step explanation. 1. The code extracts the values of P, Q, P, and Q from the parameters attribute of the result_table object. 2. It then creates a SARIMAX model using the extracted parameters along with the orders for the non-seasonal components, P, D, and Q, and the seasonal components, P, D, Q, and S. 3. The model is fitted to the close column of the data object using the fit method, and the FITIS_P parameter is set to -1 to suppress the convergence messages. 4. The summary of the best model is printed to the console. It is assumed that the necessary libraries, such as stats models, SM, have been imported before running this code. This code defines a function called plot_SARIMA that is used to plot a fitted SARIMA model and its predicted values. Here is a step-by-step explanation of the code. 1. The function takes 3 arguments: series, the dataset with time series, model, the fitted SARIMA model, and n_steps, the number of steps to predict in the future. 2. A copy of the series is created and renamed as data. The column containing the actual values is renamed as actual. 3. The fitted values of the SARIMA model are added to the data frame as a new column called ARIMA_model. 4. The first S plus D values of the ARIMA_model column are set to NaN. This is because these values were unobserved by the model due to the differencing process. 5. The SARIMA model is then used to forecast future values for n_steps ahead. 6. The forecasted values are appended to the ARIMA_model column of the data frame. 7. The mean absolute percentage error, MAPE, is calculated by comparing the actual values from index S plus D onwards with the fitted values from index S plus D onwards. 8. A figure is created with a size of 17:8 for the plot. 9. The title of the plot is set to include the MAPE value. 10. The forecasted values are plotted in red, labeled as model. 11. A shaded region is added to indicate the region of forecast. 12. The actual values are plotted, labeled as actual. 13. The legend is displayed and the grid is shown. 14. The function is called with the data frame, a best_model, presumably the best fitted SARIMA model, and a number of steps to predict ahead, 5 in this case. 15. The predicted values for the next 5 steps are printed. 16. The MAPE between the actual values and fitted values for the future steps is printed. Overall, the code is used to visualize the predicted values of a SARIMA model and calculate the MAPE to evaluate the accuracy of the model's predictions. This code creates a data frame object called comparison with 2 columns named actual and predicted. The actual column contains a list of actual values, 18.93, 19.23, 19.08, 19.17, 19.11, 19.12, and the predicted column contains a list of predicted values, 18.96, 18.97, 18.96, 18.92, 18.94, 18.92. The data frame also has an index that is generated using the pd_date_range function. The start date is set to June 5, 2018, and the number of periods is set to 6, resulting in an index with 6 dates starting from June 5, 2018. In summary, the code creates a data frame object with 2 columns, actual and predicted, and an index of 6 dates. The code comparison.head retrieves the first few rows of the comparison dataset and displays them. This code is for creating a plot of the actual and predicted closing prices of the New Germany Fund Inc. GF. Here is what it does step by step. 1. It sets the figure size for the plot to be 17 inches in width and 8 inches in height. 2. It plots the actual closing prices from the variable comparison.actual on the graph. 3. It plots the predicted closing prices from the variable comparison.predicted on the graph. 4. It sets the title of the graph to Predicted Closing Price of New Germany Fund Inc. GF. 5. It sets the label for the y-axis to Closing Price $. 6. It sets the label for the x-axis to Trading Day. 7. It adds a legend indicating which line represents the actual prices and which represents the predicted prices. 8. It turns off the grid lines on the plot. 9. It displays the plot. Unfortunately, I cannot provide an explanation without the code. Please provide the code and I would be happy to explain it step by step.